At this point in your study of geometry, you've spent a lot of time working with triangles and basic shapes such as just angles and line segments. We're now going to begin looking at quadrilaterals, and with such, we have so many more varieties of things that qualify in this category. So we're just going to take a little bit of time to learn some different quadrilaterals, their names, and some of their behaviors and characteristics. Here we have a list, so let's start defining their characteristics. First up is parallelogram, which is any quadrilateral that has two sets of opposite parallel sides. Next, we have our rhombus, which is a quadrilateral that has four congruent sides, or in other words, all sides are of the same length. Next up, we come to our rectangle, which is a quadrilateral that has four congruent angles, or in other words, all four angles are right angles. We do know that in quadrilaterals, the angles do have to have a sum of 360 degrees, and the only way to do that with four congruent angles is if they're all right angles. Okay, next up, we have our kite, which is a quadrilateral that has two sets of adjacent congruent sides. Now, traditionally, when people picture a kite, they're picturing something that a lot of people might call a diamond, but remember in geometry there is no geometric definition for diamond, but what you picture in your head of the object flying in the sky tied to a string, a lot of times is the same design of what we have as a kite. Next up comes our trapezoid, and for our purposes we're going to define a trapezoid as having at least one set of parallel sides. Now, in trapezoids, there are two different specialty categories. We're going to find one of them now and talk about one a little bit later. The first specialty is the isosceles trapezoid, and it is simply a trapezoid that has two congruent sides. Now, those sides typically are the ones that are not parallel to each other. And our last one up is a dart. Now, the dart is a bit of an interesting quadrilateral, because it is any quadrilateral that has one reflexive angle, or in other words, it is a concave quadrilateral. Now, we're not going to be spending a lot of time with darts in our studies here, but just so that you are aware of what they are. Okay, so now that we have an overall picture of what quadrilaterals are, you might see in here there are some missing, and yes, we will talk about that a little bit later, but also as we mix and match some of these definitions, we can actually arrive at other types of quadrilaterals. Okay, so just when we take a look at the appearance of some, what will come out from them? So based on the appearance of each shape, what are all the names that it could go by? Okay, so our first one that we're going to take a look at up here in our top left corner, it does appear as if we have right angles in our quarters. So based off of that, we could call this a rectangle. Now, it also has its opposite sides being parallel to each other. So in that sense, it is a parallelogram. But if it has two sets of opposite parallel sides, then it does have at least one set of opposite parallel sides. That would make it a trapezoid. And we can see that if it has one set of parallel sides, it also has a set of congruent opposite sides. That'd make it an isosceles trapezoid. And just the fact that it has four sides on its own, we could call it a quadrilateral. So we can see that based off the definitions, this figure can qualify for a wide variety of different items, just depending on what characteristic we choose to emphasize. What about our green one next to it? We can see that again we have opposite sets of parallel sides. We also have at least one set of parallel sides. Opposite sides are congruent, and it has four sides. So pretty much this qualifies for all the same things that our first figure did, except it doesn't have the four right angles, so it is not a rectangle. That would make our list look like this, which is still a lot of items to describe just this one figure. So moving down below in red, we are a lot more limited here. We have one set of opposite parallel sides. This would make it a trapezoid. However, the non-parallel sides are not congruent to each other, so we do not have our isosceles trapezoid. But we do still have all four sides, so it's a quadrilateral. That makes our list be only 2 items long, as we can see here. Now our last one, our blue figure, is going to be our most extensive. It does have 2 sets of opposite parallel sides, so it's a parallelogram. We do see the 4 right angles in the corners, so it is a rectangle. We do have adjacent sides being congruent, so it is a kite. All 4 sides appear to be congruent, so it is a rhombus. We do have at least one set of parallel sides, opposite sides congruent, so we do have a trapezoid, an isosceles trapezoid. This qualifies, and of course all 4 sides itself. This qualifies for all of our original categories with the exception of dart. And to that list, I did add one extra item, and that is square. Now, a square in quadrilaterals is a very special figure. It embodies all of the other types, like I said, except for dart, and it really doesn't have its own definition, except it's a crossbreed of everything else. And we'll talk more about how the different shapes are related to each other here in just a few minutes. So once we have the general idea of what these quadrilaterals look like or how we can classify them, seeing that there are normally many options to name a given shape, being able to specify one in particular becomes our next challenge. So here we're going to use some of our characteristics and tools from coordinate geometry. Now, early in our geometry studies, we did talk about how we could use slope and distance formula, midpoint formula to describe different objects, and we're going to do that here. So using those tools of coordinate geometry, we're going to determine the most precise name for this shape given. So to do this, the first thing I want to do is find the coordinates of my different vertices. Okay, so our first one is at the top here. I'm going to name this point. It is 3, 7. Then moving around on the right, I have 9, 4. Down below, I have 3, 1. And on the left, I'm looking at -3, 4. Now I can use these and do a number of different items. If I were to be able to determine that opposite sides were parallel, then I'd have at least a trapezoid. If I could prove that both sets of opposite sides were parallel, then I would have a parallelogram. If I could also determine the lengths of these given sides, I could have potentially an isosceles trapezoid or even a rhombus. So we have a bit of work ahead of us. First thing we're going to do is take a look at our slopes. So if you can recall, our slope formula is m equals y2 minus y1 over x2 minus x1. So if I look at my top left side, that would look like 7 minus 4 over 3 minus a -3. And that becomes 3 over 6, or a slope of 1/2. Okay, moving to the top right, so I'm going to call that first one M1, this will be M2. I would have 7 minus 4 over 3 minus 9. That would give me 3 over a -6, or a -1/2. Moving down clockwise, lower right, my third slope, I'm going to have 4 minus 1 over 9 minus 3. That gives me 3 over 6, which is another 1/2 slope. So I at least have a trapezoid, seeing as how I have 2 slopes that are parallel. Okay. And then for our fourth slope, lower left-hand corner or side, I would have 4 minus 1 over negative 3 minus 3, which gives me 3 over negative 6, which is another negative 1/2. Okay, so I do have two sets of opposite parallel sides, so I do have a parallelogram. My next question would be about distance. Okay, so if I have at least a parallelogram, it does not appear as if I have right angles, and sure enough, my slopes, while they are opposite, are not also reciprocals of each other, so I can rule out rectangle. Next question is, how long is each line segment? So to do this, I'm going to use my distance formula. Now, if you'll recall, distance formula is just a special case of Pythagorean theorem. So going in my same order as I had before, starting on my top left, distance 1 will be the square root of 7 minus 4 squared plus 3 minus negative 3 squared, which becomes the square root of 3 squared plus 6 squared. 3 squared is 9, 6 squared is 36. That becomes the square root of 45. While I can simplify this, that's going to be sufficient for what I need right now. Top right side, distance 2, I will have square root of, again, 7 minus 4 squared plus 3 minus 9 squared. That becomes the square root of 3 squared plus negative 6 squared. Now when you square a negative, it still comes out positive, and I end up with the square root of 45. So I have one set of adjacent congruent sides, therefore this is at least a kite. Now, a parallelogram and a kite, there's only certain ways that that can work, but let's finish our exercise. Finding my third slope, we also arrive at the square root of 45, so 3 out of my 4 are congruent. And then, of course, going on to my fourth, I find the same thing I did for my second, and that is a square root of 45 with 3 and negative 6 being my items to be squared. So I have two sets of opposite parallel sides, and I have 4 congruent side lengths. So best definition for this is going to be that it is a rhombus. So that distance formula and our slope formulas are going to come in handy if we ever have items plotted on a graph in order to determine exactly what shape we can make. Okay, so what if we're given a shape and then we are told what it's supposed to be? How can we use the to solve for that? So here I have a shape, and I want this to become a kite. So if you remember a kite, we end up with two sets of congruent adjacent sides. So in order to do that, I'm going to have to play with those congruences. Now my top two, if we look at the expressions that are provided, one is 2y plus 5, the other is x plus 6. Since they deal with different variables, that's going to be very hard to work with. Now my lower two that are going to be congruent, I have 2x plus 4 and 3x minus 5, which, since they both deal in x, becomes much more reasonable. Okay, so I'm going to use those in order to solve for x. If they're congruent, then that means that 2x plus 4 would have to equal 3x minus 5. Solving for x, I'd subtract 2x from each side. And then I would add the 5, so x equals 9. Substituting that back in, 2 times 9 is 18, plus 4 is 22. 3 times 9 is 27, minus 5 is also 22. So I have 22 on lower left, and 22 on lower right. Now, if I also use that same 22 and substitute in the upper right, sorry, if I use that same 9 and substitute in the upper right, 9 plus 6 would give me a value of 15. Now, if the upper two are supposed to be congruent as well, then 2y plus 5 would have to equal 15. And that would give me the opportunity to set up my other equation. 2y plus 5 equals 15. Subtracting 5 from each side, I have 2y equals 10. Dividing by 2, y equals 5. So 2 times 5 plus 5, 10 plus 5 gives me a total of 15. So I end up with 15 on my top left as well. So knowing that certain angles are supposed to be congruent, or knowing that certain side lengths are supposed to be congruent for our different shapes, we can put all the pieces together. Now, when we look at quadrilaterals as a whole, there is what we like to call a hierarchy or quadrilateral family tree. Now, in this family tree, the further down the tree we go, the more refined the shape. The higher we are on the tree, the more general the shape. Anything down below will hold the characteristics of everything in its direct line system above it. Okay, so what types of items belong on my quadrilateral family tree? Well, first up is just talking about quadrilaterals in general. So knowing that I start with quadrilaterals, what can I do with them? Now, there are different ways of organizing this family tree, and the things that we're going to be taking a look at, a lot has to do with different relationships and formulas that we'll use later on in geometry when we are talking about how to compute the areas of these shapes. So going down the left-hand side, our first stop is a kite. Okay. On one step removal, going down my right-hand side from the quadrilateral is our general trapezoid. And if you remember, we defined a trapezoid as having at least one set of parallel sides. Now, in that, we also had that there was an isosceles trapezoid. Which had that one set of parallel sides, and the non-parallel sides were congruent. There is also a specialty trapezoid called a right trapezoid. And this is simply a trapezoid where, as people typically draw them, top and bottom are parallel, and on the left-hand side, we're looking at a pair of right angles. It doesn't always have to be drawn that way. We can also draw our parallel lines going vertically and then go from there. Now, if we push the trapezoid beyond having one set of parallel lines to it having two, we could then use call this a parallelogram. Some people will abbreviate this as p-gram. Right now I'm writing out the whole name. Now, if I combine a kite with a parallelogram, so kite, two pairs of congruent adjacent sides, and opposite sides being parallel, then what we would end up having is actually a rhombus. So whatever, again, I was building this off of the idea of area formulas. Whatever formula we use for finding the area of a kite, I can also use that to find the area of a rhombus. Whatever formula I use for finding the area of a parallelogram, I can use it for finding the area of a rhombus as well. Our next combined characteristic is if I take a parallelogram, a right trapezoid, and an isosceles trapezoid and combine them together, I will actually end up with a rectangle. Okay. So rectangle shares all of those characteristics, and as such, all of their area formulas as well. Then last, and our most refined shape, if I take a rhombus for congruent sides and a rectangle for congruent angles, then I end up with our specialty shape of a square. And if you recall, an equilateral, equiangular shape is called a regular polygon. And so we'll be here, our square is our regular quadrilateral. Okay, so this is just a general overview of what quadrilaterals are, some different names and some different relationships. We'll be using these quite a bit as we go forward, and knowing this hierarchy or this family tree that you see in front of you will be very key in knowing those relationships as well.